Good afternoon. We're going to start the poster presentations now. First, I want to recognize all of the students that submitted posters and their advisors. And we know that it took a lot of effort and time and a lot of thought that you put into these. And I want to give all of the students a round of applause. We're going to show some videos of the winning posters, and honorable mention, fourth place, is flexural resistance of ultra-high performance concrete subjected to freeze-thaw cycles, submitted by Omar Yadik, Dip Bannock, and Dr. Royce Floyd from the University of Oklahoma.
Hello, my name is Omar Yadak, and I'm a master's student at the University of Oklahoma. Today, I'm going to walk through my poster and Hello, my name is Omar Yadak, and I'm a master's student at the University of Oklahoma. Today, I'm going to walk through my poster and talk about my study, the flexural resistance of ultra-high performance concrete subjected to freeze-thaw cycles. To start with the abstract in the background, UHPC is an advanced cementitious material with high durability and very low permeability, which makes it a durable material for severe weather conditions. In this study, we wanted to investigate three items: the effect of freeze-thaw on the non-proprietary UHPC called J3-UHPC, the effect of fiber content by volume after subjected to freeze-thaw cycles, and the flexural resistance of ultra-high performance concrete after the completion of freeze-thaw testing. To talk about the freeze-thaw test setup, it was according to ASTM C666. Measurements of weight, frequency, and dimensions were taken after 36 cycles until the completion of 350 cycles. In terms of the results, let's start talking about the 3x3x12 prisms. Here you can see in figure A below, it shows the resonant frequency over the course of freeze-thaw testing of all specimens. The frequency measurements show how much vibration is passing from one end of the specimen to the other. For the uncracked specimens, it shows constant frequency throughout the whole testing, which means no internal damage or deterioration happened to the HPC. However, for the pre-cracked specimens, they started at a lower frequency, and then there was an increase up to 110 cycles of resonant frequency, and then it reached almost constant frequency. That increase implied that the crack present at the beginning of the test healed to almost full recovery as water penetrated into them and reacted with the unhydrated cement. For the 4x4 prisms here from this figure, you can see that how all the specimens basically increase about 2% of the resonant frequency, indicating gain in strength, no deterioration, and continuation of hydration. For the flexural strength test setup, it was according to ASTM C1609. Initial cracking was induced until the first drop of the load deflection curve. Here, in terms of the results, you can see the load displacement curves for all the tested specimens. They both experienced, the 3x3 and the 4x4, initial linear load displacement behavior, and then displacement hardening behavior until leading to the post-crack peak load, and then stress sustaining behavior except for the no fiber specimens where the failure was sudden and brittle, as you can see from this specimen. For the results of the flexural resistance for the 3x3, from the table below, the flexural strength of pre-cracked and water-cured specimens was lower than the control specimens, but the uncracked specimens had similar strength, meaning that the freeze-thaw did not really have a significant effect on the strength. For the 4x4 here from this table, the behavior of the strength was similar to the control specimens. An increasing fiber content resulted in a higher flexural resistance. The most significant strength reduction was for the no fiber specimen, which was 49% decrease in strength, indicating that the fibers play a crucial role in resistance to extreme environmental exposure. In conclusion and implementation, this research can be further done to evaluate other types of fibers and more specimens per each fiber content, and maybe induce more significant initial cracks and compare them to different curing conditions. And with that, I would like to say thank you.
Could Omar come up? See here? Yeah. Yeah, come up for some pictures. The third place winner, importance of subsurface temperature probes in RWI systems, Muhammad Ali Habib and Hazem Rifai and Alan Stevenson, University of Oklahoma, Tulsa.
This project highlights the importance of subsurface temperature probes in road and weather information systems. We start by investigating and quantifying the relationship with ambient and surface temperature, weather events, surface conditions, and road clearance time. We aim to lead to enhanced prediction for surface conditions, weather events, and better snow clearance. Existing literature focuses on the prediction of surface temperature, which prompts the need for this study to show the significance of incorporating subsurface temperature. Existing RO stations measure a variety of weather data, including precipitation levels, which we use to get weather events, and we also got access to surface conditions, which are manually collected by visual inspection, and the RO station is equipped with 2 probes measuring subsurface temperature. We also got access to clearance data collected by a mobile application in snowplow ODOT trucks. If we look at the progression of temperature over time, we notice that they follow a specific pattern. But during snowstorms, we notice that subsurface temperature, ambient and surface temperature dip below subsurface temperature, which exhibits less variation. To understand this better, we applied a variety of analysis methods as well as machine learning models. Let's look at the correlation between probes and ambient surface and bridge surface temperature. We notice that they all exhibit a strong correlation coefficient as well as high confidence levels. We look at the correlation for subsurface temperature for different surface conditions, and we notice that there's a statistical significance difference between hazardous and dry conditions for both probes. We apply regression analysis to quantify the correlation coefficient and rate of change between subsurface temperature and ambient temperature during night and day. We notice that during the night, there's a 60% increase in the rate of change compared to its dry equivalent and 15% increase during the day. We also exhibit, the data also exhibits stronger and faster rate of changes during the night compared to day for snowy and icy conditions. We develop machine learning models that quantify the importance of subsurface temperature probes for prediction for surface conditions and weather events. We notice that when using ambient, surface, and probes, we get the best results. But what is interesting is that when we use only probes, we get better results than when we use ambient and surface conditions for predictions. Weather events show the same results. We get the best results by Model 1, followed by Model 3, and then Model 2. Clearance time has an inverse relationship with the mean of the subsurface temperature and a linear relationship with its standard deviation. We showed examples in this project highlighting the importance and the correlation between subsurface temperature and other variables. We showed the correlation with clearance time and the impact of incorporating subsurface temperature in machine learning models. Thank you.
Muhammad Ali Habib. Our second place poster, repair a bridge pre-stressed concrete girder subjected to overheight vehicle impact. Francis Ashin, Haitham Abdel Malik, Mohamed Abdulaziz, and Mohammed El Ghadi, Missouri University of Science and Technology. I don't think they were able to make it, but we're going to watch their videos.
Hello everyone, this is Francis Ashen, and today I'll talk our topic of discussion is the repair of bridge pre-stressed concrete girders subjected to overhead vehicle impact. So vehicular impact is the number 3 major cause of bridge collapse here in the US. And according to a study in 2012, there is approximately 200 collisions with bridges that occur annually in the state of New York. And this shows that there is the need to determine the best repair technique to recover the as-built strength of the damaged girders. So why therefore do we need to repair damaged girders? Number one, the first important parameter is the cost. So there's extreme cost associated with replacement, and also with replacement of girders, it is not time effective, which means that when we are replacing a girder, some portions of the road needs to be closed down or blocked, and this reduces the productivity and mobility. Also, when we should look at the durability of the cost. So today, my presentation will show how durable and cost